Okay, let's examine this problem. I first noticed that we're talking about a number 5 hours, so that's a mean. So that's going to help me develop my hypothesis here. And then I'm noticing there's the n value, 12, and they want to know if the company has met its goal. Okay, the goal is 300 minutes. So I'm going to set up my hypotheses. My alternative hypothesis is that the mean is 300 minutes. Then my alternative hypothesis, if they want to say that it lasts over 500 hours, so I'm going to do mu is greater than 300 minutes. Note that these always must have the same value. Okay, now I'm ready to do my model. First, we're going to do independence, and there are two conditions. We are going to, it doesn't state it, but we're going to assume that these are random or representative, which is kind of the same. There could be some caution about that, okay, because these are the first 12. But we'll just have to proceed with that. We also want to know that 12 is less than 10% of all potential new batteries. And then we need to test the condition that it is nearly normal. Now, we don't know the overall population distribution. We only have 12, so that's not enough to assume nearly normal. We're going to actually have to have some kind of plot of the data. This time I think the best thing, I put this data in my calculator, and hopefully you can do that too. Put it in your stat edit list 1, put in all the data, and then I went to stat plot, and I'm going to go to my first one, and I want you to select, I'm going to turn stat plot on and select the very last one. You could do a histogram, but I think many times it's easiest to look at the normal probability plot, and that's the very last one there. So I'm going to enter that. I'm going to go ahead and graph. Oh, I have got to clear out the data out of my y equals. So I need to clear that function from pre-calc. Okay, go back and graph and zoom stat. Okay, sorry about that. There is my graph, and I can see that yes, it is approximately a line. Let's go ahead and draw that here. What I want to make sure is everyone knows the labels for the axes. Well, first this is 0 right here, and this is the z-score. So this is your z's, and this is 0, and these are the positives, these are a negative. Let's go back to this. If you aren't sure what you've got, just hit the trace sometime. Oh, I can see here that my x value is 253. What is 253? Oh, well, that was the minutes that I had used, and the y, as you can see there, is the z of negative 1.73. So this is your minutes. So we have these, and you can just approximate those. That's okay. Okay, the important thing is that you do have the labels for your axes. So we've shown the normal probability plot, And what we need to say that it looks like it is linear and there are no outliers. And so from that we can say that it is nearly normal, our data. Okay, going through the mechanics, we now know that the sample size is 12. The degrees of freedom then is 1 minus that. Now I could find both of these by using one variable stats, but I think it's easier to just go directly to the test and all the data will be given for me. So I'm going to write out that t is equal to the statistic minus the parameter divided by the standard error. That formula is on your formula sheet, by the way. And now, going to my calculator, I'm going to go to Stat, go across to Test, and the test that I am doing is the t-test. So in this case, since we have our data, we'll just go directly from that. We won't calculate the data ahead of time. Then I'm going to put in 300. My data is in list 1, that's the frequency, that's greater than, and then I'm going to calculate. And this screen then gives me everything I need to use, okay? So it is giving me my X bar, or my sample, right? That's the 306. It gives you your standard error, that's 29.31. So I can go ahead now and fill these in my t calculation, 306.25 minus the 300, which is the population parameter that we're testing, the null hypothesis, divided by 29.31, divided by the square root of 12. And then that should give me my t statistic, which is got here is 0.74. And then I want to know the probability that t is greater than 0.74. That is also given right here. That's the p that's right there, 0.24. So since that's a very high value, we will fail to reject. The 0.24 is greater than any alpha. It would be greater than 0.1. I'm noticing here we forgot to state up here that we wanted to use a student T model. And the reason why we're using student T is that we have two sources of variation. We do not know either the population mean or the population standard deviation. When we have the two sources of variation, we must not use just the z but go on to the t. The z is okay if we just have one source of variation, just the mean, and if we knew the standard deviation, but that's rarely true. So we're going to use the student T model, and we're going to use a one sample t-test. Okay, so now let's go ahead and write our conclusion. Since the p-value is large at 0.24, we fail to reject. There is not sufficient evidence that the battery life has increased to more than 300 minutes. Notice this always must be given in context of the problem. That's why I'm talking about the battery life. Okay, the next thing it asks you to do is to find the 90% confidence interval. Okay, so if you look at your formula sheet, you know that the confidence interval is the point estimate plus or minus the margin of error. And the margin of error here is going to be the t star. And I'm going to put a little 11 underneath as a subscript because that's how many degrees of freedom there are times the standard error. Well, we already know our point estimate. We have that from the prior problem. It's 306.25 plus or minus. Now I've got the standard error, that's up here, 29.31 divided by the square root of 12. I need to find my t star. To do that, what I'm going to do is go to second distribution and go to inverse t. And since I want a 90%, and I think a lot of students kind of got confused on this, if I want a 90% interval, 90 this way, what I'm looking at here is the 0.95 as the upper t value. So I'm going to put in 0.95 here. The degrees of freedom we said was 11. And I'll go ahead and calculate that. And there's my t star value, 1.796. And I could go ahead and do those calculations, or I could also just have my calculator do the work for me. So I would make sure I didn't have any errors. So I would go to Stat, go to Test, and you can see there's number 8 is the t interval. And I'll go from the data, I'll keep that. My confidence level I've got as 0.9. I like this because it's so quick using the calculator, and also I'm sure that I don't make any errors this way. So I can go ahead, there's my 291.05, comma 321.45. Okay, and so we need to write a conclusion. So our conclusion would be we are 90% confident that the true population, that's the critical word here, population mean battery life in context is between 291.05 and 321.45 minutes. Remember, you are always doing the confidence interval about what the population mean could be. You know what the sample is. Your question is, what is the population? Okay, and then the last step is to figure out if you wanted to do another trial but you wanted to be 95% confident between plus or minus 15 minutes, how big a sample would we need? Well, we've done this in the prior unit. We have a problem now with the t star because we need to be doing figuring out n, but we need t to figure out n, and then we need n to figure out t because t depends upon the degrees of freedom. So what we do is we start by doing z star, getting a good estimate of what n is, and then improving our estimate with the t t-value. Okay, so we're going to start with our z star. This is the number you would have for a 95% confidence interval. So I'm going to do that my margin of error is equal to my z star times my standard error. So my margin of error, they tell me in the problem, is within 15 minutes, so that's the 15, equals the z star of 1.96 times the standard error, so that's the 29.31, divided by the square root of n. Going ahead and solving that, right, I'm going to multiply through by square root n, so I get square root n, and then I'm going to divide by the 15, so I get this is 1.96 times 29.31 divided by the 15. And then since this is that, I'm going to square each side, and then I get an n when I round up of 15. So now what I can do is repeat this process but using the correct distribution, which is a t model. So if my n is 15, I'll have a degrees of freedom of 14. So go ahead and use inverse t. Let's do that. Second distribution, go to inverse t. And since I want a 95% interval, I want the top value to be 0.975. Degrees of freedom is now 14. And I'll do that calculation. And I end up with a value of 2.14. Okay, so now I can repeat. 15, which is my margin of error, is equal to 2.14 times 29.31 divided by the square root of n, and then I get the square root of n is 2.14 times 29.31 divided by 15, both sides squared, and now I get n equals 18. Okay, hope that works out for you. If you have any questions, please don't hesitate to email.